Okay. So, we were talking about tensor products. We showed that tensor product is left exact, right exact, and it is tensor product is not left exact. It is not very difficult to see. So, what is meant by it is not right exact, sorry, left exact? There exists, I mean, if I can find some module, I mean some exact sequence such that this is exact, but m tensor n to m to sorry m tensor n to m double prime tensor n to 0 is not exact. If I can find something like this, that will say that it is not so. Again, when we are dealing with exactness, we know that it is left exact. So, if you just hide this much, this exactness will imply this exactness. That is what we proved last time. So, if we have to say that it is not left exact, we only have to say that this map, there exists an exact sequence where this is injective, but this is not injective. So, this portion does not really play a role. So, we only have to say that I can find something like this, but that is very easy. If you look at z to z, this is multiplication f of n equal to 2n. Okay. Take the multiplication by 2 and take n to be equal to, so your a and m prime all are z, n is z2, z mod 2z. Then what do we get? Here we have z tensor z2 to z tensor z2. This is map is f tensor 1 bar. What is the image of f tensor 1 bar of any n tensor 1 bar? This would be 2n tensor 1 bar, but what is this? You can write it as n times n tensor 2 bar, which is 0. So, therefore, this is 0. This implies that f tensor 1 bar is a 0 map, but is this is not 0, right? Z tensor z2 is not 0 map, 0 module. One z tensor z2, this is non-zero, and f tensor 1 bar is 0. This implies this f tensor 1 bar is not injective. Okay. So, this says that the tensor product is not left exact. If a module satisfies the property that for every exact sequence this is exact, then that module n is called a flat A module. So, let me if an A module n, the sequence 0 to m prime to m to m double prime to 0 is exact implies 0 to m prime to n to m tensor n to m double prime tensor n to 0 is exact, then n is said to be for A modules m prime m double prime, given any A module with this exact sequence, the tensor product is exact. Then n is said to be a flat A module. It is said to be a flat A module. This is some immediate examples of flat A modules. Can you think of a flat A module? This is exact implies this is exact. Tensoring by. So, if I in particular if you start with, suppose I take A, n equal to A, m prime tensor n m prime tensor A is m prime itself, that is what we proved last time. So, this exact sequence will be same as this exact sequence. So, this exact implies this exact. So, A is a flat A module. More generally, A power n is a flat A module. Right, because m tensor A power n, what is this isomorphic to? We have m tensor A direction n times. We have seen that m distributes tensor product distributes over the summation, therefore, this is m tensor A direction m tensor A direction and so on. So, this is isomorphic to m n copies of m. So, here what would be the map? If I have f, it will be, if this is f and this is g, then this, if n is A power n, this would be simply n copies of f and here simply n copies of g. Therefore, if an element is 0 here, f of it will be a particular f of that particular element will be 0 and we will have corresponding elements being 0, because f being injective. Okay. So, this is a flat A module. We will see more examples of flat modules little later. So, to start with, we will just look at one characterization of flat modules. For an A module n, the following are equivalent. N is flat, 0 to m prime to m double prime to 0 is exact, implies m prime tensor n to m tensor n to m double prime tensor n to 0 is exact. Zero to or m prime to m is injective, implies f tensor 1 from m prime tensor n to m tensor n is injective for finitely generated modules m prime and m, f from m prime to m is injective. For finitely generated modules m prime and m, if this is injective, then f tensor 1 from m prime tensor n to m tensor n is injective. So, the main thing here is that one if and only if 2 is the definition. Okay. One if and only if 2 is definition. That is how flatness is defined. How do you say 2 if and only if 3? We are using that tensor product is right exact. So, given this, if I have a sequence, the right exactness is already given to you. So, you only have to worry about the left exactness. That is what the statement 3 is. So, this is tensor product is right exact. Okay. 3 implies 4 trivial. If it is, if that statement holds for any module, it should particularly hold for finitely generated modules. So, only statement that we need to prove in this is 4 implies 3. Okay. This one, if this is injective, then this is injective is what we know. Now, to prove 2, suppose this is given. Now, we look at this corresponding exact sequence. The right exactness of the tensor product says that it is this is surjective and kernel of this map is equal to image of this map. So, only remaining thing is whether this is injective or not, that is given by this one, third statement. Okay. Now, to say 4 implies 3, we need to say that, see here the fourth statement says that you only need to check the left exactness for finitely generated modules. Within the category of finitely generated modules, if the tensor product is left exact, then the module is flat. By definition, you need to check in the category of A modules, but the fourth statement says that you only need to check within the category of finitely generated A modules. So, suppose the fourth statement is true and I have let f from m prime to m be injective, okay. Then I have, and let us take an element u in the kernel of f tensor 1. I want to say that f tensor 1 is also injective. Suppose I start with an element in the kernel of f tensor 1. So, that means that f of u, which is equal, sorry, f tensor 1 of u, which is equal to I from 1 to n, f x I tensor y I. So, here I am taking x I in m prime and y I in n. Okay. See, I need to bring in a finitely generated module. How do I bring in finitely generated module here? I want to think of f as a map from a if I can think of f as a map from a finitely generated module to a finitely generated module, then I can say that its corresponding tensor product will also be injective. So, what is the obvious possibility here? See, see right now my aim is only to show that u is 0. Okay. So, let me take m naught be the submodule of m prime. So, let me write this m naught prime be the submodule of m prime generated by x 1 up to x n, these elements. Okay. And this element f x I tensor y I, this is 0. Okay. See, we have already proved that if I have a linear combination of tensor product equal to 0, then there exists a finitely generated module, finitely generated submodule of the corresponding modules such that the tensor product is 0 in that module. See, we have what we have seen earlier was that a tensor product is 0 does not mean that if I take an element its representation is 0 in the module m tensor n, does not mean that its representation is 0 in every submodule. We had that example of 2 tensor 1 in 2 tensor 1 bar in z tensor z2 and 2z tensor z2. In 2z tensor z2 it is non-zero. Okay. So, therefore, this, but we showed that if such a linear combination is 0, then there exists a finitely generated submodule such that this representation is also 0 in that. Okay. So, there exists a finitely generated submodule m naught of m. I will put one more condition containing f of m naught prime. So, I will put two conditions here, two finite generation conditions. One is the finite generation condition coming from the proposition that we proved earlier, and this is m naught prime is finitely generated. So, f of m naught prime is finitely generated. Therefore, I can take, in fact, if I just take f of m prime, f of m naught prime and the finitely generated submodule the existing finitely generated submodule here, taken there, they can take we can take the sum and take m naught to be that one. So, let us just take the finitely generated submodule m naught of m contain f of m naught and such that summation f x I tensor y I is 0 in m naught tensor n. In this module it is 0, in this submodule it is 0. So, let u naught be equal to summation x I tensor y I from 1 to n as an element of m naught prime tensor n. I mean, you can just see they have, as we said, they could have different representations in different submodules. So, I just take it as an element of m naught tensor n, this is. Now, restrict f to m naught prime, then f restricted to m naught prime is a map from m naught prime to m naught. because M naught is the module, a finitely generated module containing f of M prime, M naught prime. Then this is injective. Therefore, f restricted to M naught prime tensor 1 from M naught prime tensor n to M naught tensor n is injective by hypothesis. The fourth hypothesis says that for finitely generated modules, if this is injective, then this tensor is injective. But now f restricted to M naught prime tensor 1 acting on u naught, this is 0. Right? That implies that u naught is 0, because it is, this is injective. This implies u naught is 0, but now this is 0 in the submodule. If it is 0 in the submodule, it has to be 0 in the module, because it is, some element is 0 implies you can, this is in the quotient module. So therefore, that has to be, I mean, it does not matter whether you are considering it here or here, this 0 will imply the map, the element u is also 0. So therefore, this says that f tensor 1 is injective. So this, as we go along, we will see more examples of flat modules. Right now, what we know is the free modules, okay. They are all flat, that is all we know. We will see more examples probably even today. Another concept of important concept in competitive algebra is of algebras. This is pretty similar to rings, but it will have one more structure, that let A be a ring and B f from A to B be an be a ring homomorphism. Okay. Then this B can be thought of as an A module. How do you do that? Define an A module structure on B by defining the scalar multiplication as A times B equal to through the map F, F A times B. Okay. So therefore, B has a ring structure as well as an A module structure. So any ring B with a homomorphism like this is called an A algebra. Along with an A module structure via F, then B is called an A algebra. So, this is a trivial example is any ring is in Z algebra. It has, we know that it has a ring structure, and any commutative ring is a Z module. We have n times. So, I have a map via Z going to any ring A is in Z algebra. This is n going to n times 1. We have this this map is called structure map. In fact, when we say B is an A algebra via the structure map F. Okay. So, with the structure map n going to n times 1, this is an A algebra. Any ring is an A algebra. If A is a field, then your ring map will be a ring homomorphism from A to B. If it is non-zero, it is always injective. Okay. So, you will always have, if A is a field, your A algebra will always contain a copy of A. Okay. Then F from A to B, assuming it is non-zero, is always injective. Therefore, B has a copy of A. Okay. Any K algebra will contain a copy of K itself. Some of the familiar K algebras, or A, in fact for any ring A algebra, X alpha polynomial ring over polynomial ring in what some variables over A is an A algebra. So, in this case also we have a copy of A inside this, A going to this, the inclusion map is injective. Okay. So, this is an A algebra. In fact, more generally, if I have an ideal, let I be an ideal, then this is also an A algebra. In this case, this A to this one, A to A x alpha mod I need not necessarily be injective. For example, if your ring A is Z and this is A algebra is Zx, and you take ideal I to be 2 comma x, then this map is not injective. A to A Zx mod I is not injective, right. So, these are some examples of algebras. If A if B is an A algebra, which is a finite A module, then B is said to be a finite A algebra. There are two terminologies, one should be careful, and if B is if every element of B, if every so let B be an A algebra, with the structure map F from A to B, then B is said to be a finitely generated A algebra if there exists, okay, I will simply write like this, there exists an onto ring homomorphism H from A polynomial ring T naught up to N to B. That means I can write B as a, see I mean I can find finitely many elements here such that every element of B is a polynomial on this with coefficients coming from f of A. Let me write down, that is there exists x1 up to xn in B such that each element of B is a polynomial in x1 up to xn with coefficients from f A. We can write A or f A, because when you write A, by definition it will be f of A. Okay, T1, or in other words B will be some finitely generated polynomial ring modulo an ideal. By first isomorphism theorem, if I have a ring onto ring homomorphism like this, B is isomorphic to this modulo. So, if I have this is okay, so for example Z x1 x2 modulo x1 square, this is a finitely generated Z algebra. Is this a finite Z algebra? Is this a finite Z algebra as a Z module? Can you tell me a generating set for this? B is this. Can you tell me a generating set for this as a Z algebra or Z module? I will have one, of course, one bar, I will denote by bar because this is a quotient ring modulo. I will have x1 bar. See, if you take this Z x1 x2, can you tell me a generating set for this as a module over Z? As a module over Z? Okay. Can you tell me as a vector space over Q what is its generating set? As a vector space over Q, is this finite dimensional? So what is its can you give me a basis? X1 x1 square. Can you be can we be little more? Yeah, so I can simply write x1 power I x2 power j I plus j bigger than or equal to 0, right. This is a basis. Now can you give me a Z module? As a Z module, what is its generating set, minimal generating set? This will work, right. This will again be a Z module generating set, right. So when you take a quotient, see you are basically nullifying some of them, right. So which all will remain in a minimal generating set? x1 x1 x2 x1 x2 j, yeah. So x1 power I x2 power j, what is the condition on I and j? 0 less than equal to I less than equal to 1, 0 less than equal to j, right. So this is also, this is as an Z module, this is not finite, but this is a finitely generated Z algebra. So this is not a B is not a finite Z algebra, it is a finitely generated Z algebra. B is not a finite Z algebra. And if I take Zx modulo x cube as a Z module, what is its, can you give me a generating set for this one? Right, this is an Z basis in fact. So therefore Z I call this B. B is a finite Z algebra. Just wanted to give an example of a finite Z algebra and a finitely generated Z algebra. The first one is a finitely generated Z algebra which is not a finite algebra. The second one is a finite algebra. If it is a finite A algebra, it is automatically a finitely generated A algebra, because here we have finitely many elements whose linear combination is a linear combination gives the whole ring, that automatically gives all polynomial combination. So if B and C are A algebras, okay, then B tensor C, this is an A module. As A modules I can take tensor products, right. This is an A module and this this has a ring structure by taking the multiplication. Okay, so let me write down this definition of B tensor. See, this has a, this is an A module though, so this has a addition in place. Now if I take B tensor C B prime tensor C prime, I define it to be B B prime tensor C C prime. Okay. So with this multiplication, B tensor C is an A, as is a ring, and hence an A algebra. I will leave the easy verification to you to complete this. We will see more of A algebras later, but now let us move on to study what is called localizations. So localization is a process that we generalizing the construction of Q from Z. So how did we construct Q from Z? We look at this set Z cross Z. I take some A comma B. I say that this is equivalent to C comma D if, so I mean see, with this I have I have in mind A by B and this is C by D. When do I say these two are equal? AD minus BC is 0, right. But here we have one more condition, that neither B nor D is 0, right. B is non-zero, D is non-zero, or in other words the second component is in fact Z without 0, right. We are taking this cross product and putting this equivalence relation on this set. Okay. Now we imitate this and do it in the case of general rings. So in the case of general rings, we want to move ahead from A and get to a place where we have more units. See, in this, by this construction, then we prove that this is an equivalence relation and say that the equivalence class is basically Q. Okay. So in general the idea is we get a ring containing A which has more units. Okay. So the idea is this: let A be a ring, a set is said to be multiplicatively closed said to be a multiplicatively closed set if one belongs to, so a set S, one belongs to S and A comma B belongs to S implies the product is in S. So what we will do is, taking a multiplicatively closed set, so I take, look at this S cross A, define a relation on S cross A, S comma A is same as T comma B if AT minus BS is 0. This is what we want. Ultimately, what is that we want? We want to say that A by S is same as B by T. Okay. But again, there is one more small, or in other words, we want to say this is 0. I mean, our aim is like this, but this is TA or AT times BS divided by TS. Okay. But at the same time, see, I want A by S equal to B by T. See, I should also get this is same as some AT prime ST prime. This should be equal to this as well, right? Or in other words, AST prime minus, so here, so let us now look at this condition. This says that BST prime minus ATT prime, this is 0, or in other words, this is 0. In the case of Z, this 0 will automatically imply that this is 0, but yeah, S, oh sorry, S is a subset of A. Yeah, we are inverting elements of S, some some elements of A. Okay. So, in the case of Z, once you reach here, this will automatically imply this is 0, but in the case of general rings, this does not imply that this is 0 if it is not an integral domain, right. So, when we are doing this process, when we are making this relation, this is probably not enough if we want to say A by S is same as B by T same as AT prime by ST prime. What we want is, if I can find some U such that this time is for some U in S. Okay. We are not saying that right now, that will be a corollary. If I have 0 in that, we will see what happens to this process. Okay. So, this one, let me stop here by saying that this is an equivalence relation. Okay. We will continue from here next class.